So in my remaining 5 minutes or so, I'm going to very quickly try to go through some of these apps in some more detail, just to give you an idea of the technologies that are involved. So in smart parking, and you see here just a picture of our app, which we have implemented at Boston University, the motivation comes from this particular quote, that 30% of vehicles on the road in any downtown major city are cruising for a parking spot. So 1 out of 3 cars basically is looking for a parking spot, and it takes an average of 7.8 minutes just to find a parking spot. So you see that the problem of parking is not just a peripheral one, it's central to our traffic woes. And right now, there are some guidance-based parking approaches, but there are serious drawbacks because, first of all, you may not find an empty space, you may miss a better space, and also there's a lot of processing done while you're driving, which could be dangerous. So from the city standpoint, you have an imbalanced parking utilization, and in fact, any kind of so-called smart parking today that guides you towards an area where there might be good parking, in fact, can add congestion. Because imagine if about 50, 60 drivers are all told that there's a couple of parking spaces in this area, then they all converge there, and you create a bigger congestion problem. So our idea is to convert the problem of competing for parking, which is what the state of the art is, into an automated process where we're no longer competing, but we're in a sense collaborating with each other. So here's a picture of the downtown Boston area, and on the bottom left you can imagine a car approaching that area and simply using a simple interface, simply saying, I would like the best parking spot for me for my current destination, point A. And the system finds the best parking spot for this driver in the following sense. It is the shortest distance from the actual destination and provides the least cost, street parking versus garage parking and so on. And in addition, it reserves it. How do we do that? We do that by addressing each one of these 4 technical issues with the available technology that we have. First of all, on the parking space availability detection issue, it is relatively easy to use standard sensors and wireless sensor networking to detect that. We use GPS for localization. We use smartphones and the existing vehicle and navigation systems for communication. And finally, on the reservation side, we use kind of a red, yellow, green little system, which you can imagine sitting on top of a parking meter, for example. The green indicates that a parking spot is available. The red indicates the parking spot is reserved. And the yellow actually invites the driver to go and park there. So this is a picture of a downtown Boston area that we used for a case study just to lead to these basic results, that you can achieve 10 to 20% higher parking utilization. You can virtually eliminate the percent of drivers that are frustrated, wandering around looking for parking, and you can achieve as much as a 50% reduction in the parking time looking for parking under heavy traffic. Now, switching to the street bump application, the idea here is to detect obstacles for free, essentially, because everybody has a smartphone. In this particular app, we use an iPhone that has an accelerometer and has a GPS. So there's no infrastructure needed. And this actually is an important point in creating smart cities. We'd like to use technologies that minimize the need for additional infrastructure, therefore cost. The data that we collect from anybody who has a smartphone in their car from the Street Bump app goes to a central server, and then we process the data and run some fairly sophisticated machine learning, optimization algorithms to detect what so-called anomalies and to identify and classify the obstacles. So in the picture here, you see that there are some so-called actionable items. The leftmost shows a really nasty pothole in Boston. The rightmost picture shows an obstacle that would be detected. It's great, but there's nothing wrong with it, and it's not really an obstacle. And this is an example of how you can then process all this data. This is a big data application, really. And you can then prioritize the different actionable potholes and so on, and convey this information to the city. This is an example of the kind of technology that we use to perform this anomaly detection, taking advantage of the fact that a non-actionable signature of the vibrations that you see on the left plot looks like this, looks pretty normal, a nice smooth oscillation. But if you go over a pothole or another nasty, unnatural obstacle, you get completely different signatures. So the idea is to use interesting algorithms that can differentiate between the left picture and the right picture and notify you about the right picture, and then some additional work classify the obstacles. And as a result, we can provide a list like the one you see on the right. So for instance here in something that we did in Boston, we were able to classify the top 10 worst obstacles on a given day, and we only missed on one. There's only one out of the 10 that was not actually a high priority obstacle. Now, on the traffic light control side, I just wanted to mention, if you look at this picture, that it's very frustrating for a typical driver that goes down a main avenue like the one that you see here, which happens to be Commonwealth Avenue in Boston, and then have to stop and stop and stop and stop as the car arrives at different intersections when, for example, there may be no traffic on the smaller perpendicular roads. Instead, you would want the car to do something like this, by taking advantage of the fact that the traffic lights can communicate with each other, and they can change the red to green accordingly, so that you can adapt the red-green light cycles based on the real-time data that you have. As a result, you can predict and alleviate congestion, not only over a couple of blocks, but potentially over an entire network, reduce waiting times, therefore congestion, with the extra benefit of reduced pollution and waste of fuel. The more general traffic control problem, which we all know about, comes from the fact that really there are two main problems which prevent intelligent engineers from solving the general traffic problem. The first is that there's just not enough controls, and that prevents us from use feedback control, which we have so successfully applied in many other applications. The second reason is that we don't know the other driver's behaviors. This comes from an elementary game theory that says that if you don't know how the other players, the other drivers behave, you make bad decisions. And this creates this gap between individual, selfish behavior and system-wide or socially optimal behavior. The gap is called the price of anarchy. And part of what we have done, and there's a paper in the proceedings special issue, which is indicated at the bottom here, which actually measures the price of anarchy. And for data that we have from the Boston area, shows that the price of anarchy is as high as 2. It's a ratio, actually. So 2 really means, the ideal is 1. The ratio of 2 means that we could reduce congestion by a factor of 2. And how can we do that? Well, the opportunity is the connected, automated vehicles that are emerging now and that create what we call the Internet of Cars. So the Internet of Cars is something that in urban mobility is intricately related with smart cities. And my last slide is to show you what happens if you use this connected automated vehicles in a really, really complex intersection in downtown Boston. On the left, you see a simulation showing what happens with traffic lights. So you see cars queue up and occasionally stop when they encounter a red light. On the right side, we have eliminated traffic lights. There is no need for traffic lights if you can control vehicles automatically to always flow through and never stop. And we have shown that there are significant benefits to doing that. Of course, there are many technical issues associated. And I want to thank you with that, and also thank all of the sponsors of the research that we are conducting on smart cities. Thank you.